Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So now it is my pleasure to introduce our keynote speaker for this morning, Yosef Khalidi. He is a distinguished engineer at Microsoft and working in the Azure group. Prior to that, he had a distinguished career at Sun Microsystems, where he was one of the architects of the Solaris operating system and the Sun cluster. Solaris is an old favorite operating system of mine, and probably many of you used it as well. So it's really fantastic that we have him here for this event. Yosef.
So good morning, everybody, in the room and online. My name is Yosef Khalidi. Can you guys hear me? Good. Good, thank you. I have an hour or so this morning. My intention is to discuss with you some of this cloud stuff we're all sort of active in nowadays. I want to start with give you a bit of background of what I have been working on in this space, and then if you will segue in what some of the issues we see in this space and how we have been solving some of them. And at the very end, I'll tell you more about some opportunities, some open, perhaps research issues we can go all address. I've been working in Windows Azure since the beginning, actually from day -1, before we even called it Azure. And frankly, before the word cloud was actually in fashion. We started it by building a large-scale, very large-scale web application hosting platform, if you will, which over time we evolved into this very large public cloud that we all know today. But for today's presentation, I want to follow a format similar to the one behind me here, which is talk a bit about the promise of cloud computing and the value proposition, exactly like one slide, guys. I will not rehash the old stuff. But more interestingly, repeat the message that without large-scale, cloud computing promise cannot be achieved. You need to have very, very large scale. Scale, there's a number of machines, large networks, and so forth. I would hammer the point a number of times. With that, though, you have a number of challenges. Challenges of security, isolation, performance isolation, a number of issues like that. Then I want to switch and tell you concretely how we have been addressing some of these challenges and where we have not yet addressed them, and some opportunities to go forward from there. Sounds good? You can stop me with questions toward the end. I'm fine with either way. So the one marketing slide I have in my presentation, if you want. Nice slide. And just make sure we're all anchored in the same space here. Cloud computing, in our definition, if you will, is about this delivering of a big illusion of huge computing resources over the internet as a service. Some speak of it as delivering IT as a service. It's effectively getting your compute resources, network resources, as a service from somewhere else. The location where the cloud is not very relevant, really, to us. I mean, it could be at some public data center, like Windows Azure or Amazon, for example. It could be some other variation, other places as well. The point, though, as you see time and again, you need scale to make all these value prop we all know about actually come through. If you want to talk about elasticity, scale up, etc., you need to have a large pool of resources to which you can get your resources from. You need to have a big ecosystem to share the resources between them as well. We see the universe, frankly, moving this way, the computing universe, if you will. Very much devices that all of us are carrying, and I bet you each one of us here have at least 2 devices of this nature, maybe a smartphone, a laptop, maybe more tablets, what have you. And we all know that the stuff we carry nowadays is only as good as what you get from somewhere else. We're seeing this in the business. We're seeing the computing industry at large. More and more smart devices everywhere, requiring very highly available, highly continuously available services up in the cloud somewhere else. And a device space, as you know, could be the devices you and I carry all the time, a phone, a laptop, whatever, or it could be almost anything with an IP address. These buildings, maybe this is a bit old building here, but newer buildings, if you will, typically have stuff. They have temperature sensors. They have air conditioning equipment. Data is being generated like crazy from all over the place. But these systems are not really autonomous, if you will. They require stuff in the back, which is where the cloud comes in. So all our energy, to be honest, has been making this slide, if you will, real. And the cloud stuff we're talking about this morning is about the left-hand side of this slide. Let's go architecture for a second. In our mind, if you want to build a large-scale cloud system, you have to follow those 6 architecture tenets behind me, if you will. And I claim the same applies whether you have to build something like Windows Azure, or you're building something like Amazon EC2 and S3. All of them have very similar characteristics, architecturally speaking. And there are. The first one is, of course, virtualization. We all have hardware, compute nodes, servers in these systems. You need to be able to slice and dice them for a couple of reasons. One reason is for resource allocation, of course. Yeah, they're a physical box, and you may need to slice them in smaller pieces in different dimensions between memory and CPU and bandwidth, depending on the problem at hand. So that's one reason why you need server virtualization. The other reason, of course, is for security, really. You need some trusted component in every physical server, which you will do isolation of those elements, both within the server and in the network as well. You can do isolation some other ways, perhaps in hardware. We very much believe the way you do network isolation is in the machines themselves. Which leads me to my second point. You have to also virtualize the network. So it's one thing you have all these virtualized computing elements all over the globe, all over the network, if you will. But they have to talk to each other. And as you probably know, classical networking, where you actually go and buy a switch and wire it and do the classical things, set up a VLAN, what have you, are very nice static systems. And here we're talking about dynamic systems, really. Systems where an application demands different topologies rather frequently. So you have to have also a virtualized network. And by the way, as I move on, I'll then go back to the slide and tell you how I actually implemented every box here. So for now, bear with me. Think of it as a tenant or as a requirement, if you will. Another one is, with cloud computing, we're talking about so-called scale-out computing. We're talking about horizontal scaling, not vertical scaling. Don't get me wrong. At any given point of time, your cloud provider will buy machines, whatever good cost performance in the market nowadays, number of cores, etc. But ultimately, you want more scale, you'll get more of them, not bigger of them, if you will. So about horizontal scaling. And typically, the unit is some virtual machine size of some sort. Some combination of memory, CPU power, some network bandwidth, etc. Which has implications, of course, on the apps, on the services that we all write in this environment. Okay? Do note a small thing I have in the slide here, which is optimizing for mean time to recovery. It's really key, guys. And this is true more and more if you want to write very highly available services here. In these systems, expect failures. In these systems, you have a sea of machines, physical, virtual. We're talking really many of them. And you don't have humans watching every box to make sure it's up and running and it's tightly managed. And it's not a mainframe. These are lots of machines. Failures happen. Expect them. Expect them in the hardware, expect them in the network, expect them in the software. And the key design point is to optimize for fast recovery. Don't optimize for mean time to failure. Don't optimize your application to spend a lot of time initializing and make sure everything is nice and clean. Hit the ground very quickly, because you may have to do it again. Again, all the ideas, but we have to remind ourselves of them when we build these systems. It follows, therefore, every machine in these systems have to be viewed ultimately as a cache. There's no golden machine anywhere in any of these machine systems. That is, at any given point of time, any of them can go up in flames, which means the state has to be externalized. The state of your application, the state of the system has to be able to live in the network at large. You know what that means, replication, etc. But the point is, do not assume that any machine can be kept up forever or maintained, especially if you will. Everything's a cache. And if you believe the story, the only way you can actually make it work is through automation. Just imagine having tens, hundreds of thousands of servers. Can you imagine having humans running around and patching the OS or configuring the network or configuring the application? Of course not. So you have to have automation. And how do you do automation? There are a number of schemes. I'll touch on some of them in a second. And lastly, as we all know in this room, and I'm sure online, writing distributed systems is very difficult. Most programmers, frankly, have difficulty with multi-threading. Tell them go do replication, distributed systems, handle mean time to recovery, and the like. Life becomes very, very complex. So you want the platform to have much of the plumbing done for them. You want the platform to have a set of rich services, replicated file systems, caching services, queuing, stuff that we all need to write applications. Hopefully done one time, done by somebody else, debugged, scaled, and so forth, so that most developers, most programmers should worry about their problem, not about computer science problems of difficult nature. When we started with Azure, by the way, these were the tenets we started from. And we can debate small points up and down, but by and large, you need to have this in the mix to have a successful cloud system. Okay. I mentioned this already. I'm going to say it a number of times. To make the story gel, though, however, to get the value proposition and to get the return on investment of investing in these systems, you need scale. Why do you need scale? Remember the value proposition, guys. You can have an application. I want more capacity. You ask for it. You don't want the capacity, you give it back to the pool. Your business spikes, etc. You know the story. All this implies a large number of machines. But for a cloud provider to make money in this space, they have to effectively act like an insurance company. I'm a techie, I'm not an actuary, so maybe I'm a bit off a bit in my analogy, but you need a large pool of resources that you share effectively between a bunch of people. You may want at the moment 1,000 VMs, she may want only 10 this moment, and vice versa. I can assure you, I have slides, but not for this presentation, from a business side to show you businesses have very much a seasonal nature of things. During the day even, of course, weekly, monthly, and at certain times during the year. In many other sciences as well, there are peaks and valleys of design, of need of capacity. So the way your cloud provider can handle this thing is by having a large-scale system, over-provisioning a bit, if you will, and hopefully, statistically speaking, have enough capacity for everybody. But that means at any point of time, company X and company Y, who may be competitors, may be sharing the same cloud. They could be sharing the same physical machine. Therefore, you have to isolate them. And therefore, the discussion we had earlier about virtualization, both at the network and the server level. To be able, another point here, to get all this scale here, the illusion has to be, by and large, that of a uniform system. Now, don't take me literally. It's not exactly uniform. You have different sizes of VMs and so forth. But has to be rather uniform here. If your app requires, I'll make this up, 16 gigabyte memory and this kind of GPU and this wire and this and that, you know, it may not fit in a public cloud. You may want to buy a bunch of machines and do your own special thing. You'll find out in these systems they are fairly uniform. We have some specializations, special clusters, faster machines, and so forth. But by and large, you need to end up with a model that's that of a horizontal scaling, where the units are a small set of fixed sizes. If you want to customize quite a bit, you'll find out large-scale clouds are not really appropriate for customization. If you want to use utility computing models, if you will, where you go and ask for resources and you find a bunch of them, you'll be forced to fit a certain model. So uniformity is important. Lastly, as my last point in the slide shows, says at least, virtualization is necessary for the reasons we discussed already. But it's actually not sufficient. There is more than just virtualizing the computation there, and I'll explain a bit more in a second as well. Okay, so remember, guys, the key point here is this. We all believe in the value proposition of the cloud, elasticity, economies of scale, increased utilization, what have you. The only way this actually really makes sense if you have scale. If the cloud provider standing behind this value proposition has scale to meet the demand. But with the scale, we have to share. I cannot dedicate resources to one of you forever or for a long time. We have to share them. With sharing, you have to do isolation, etc. Okay, so let's talk about some of the challenges now. And this is why I say virtualization alone is not enough. And I'm touching on 4 areas. There are more challenges. There's not enough time to discuss everything here. One is, what does it mean for an application to be cloud ready? What does it mean to target an application, either to develop it or to port it or to move it somehow to the cloud? You'll find out easily that a forklift approach typically does not work. Yes, I can take a piece of code, put in a VM, run it in a cloud, that's nice and dandy. But you want to make it scale out. You want to make it highly available. You want to really make use of the elasticity of the cloud. You'll find you have to do extra work in there. And if you happen to be looking at something like an enterprise application with some dependencies on data and so forth, you may find out that you have to keep part of it still on premises or somewhere else for a plethora of reasons. So one area I'll touch on is, what does it take to target an application to the cloud? How do you write these apps? What service do you need to write them, and so forth? Another area, of course, is security. And I know security is, in general, an important umbrella. It's actually doubly so here, because all the sharing points I made earlier. Again, you and your competitor, if you're 2 companies or 2 groups, could be running on the same infrastructure here. Not only do you have to trust your physical security of your provider and so forth, but you have to have assurances that the right isolation is being done. Isolation for data privacy, even performance isolation between the different pieces as well. So security is a big deal. The third one sort of follows in a sense, which is for 2 reasons. One is, the third one is about compliance, really. What are the rules that govern the operator of this system? And how do you know that the operator is following them? Who has access to your data? All the operators, etc., all the management and so forth. And in a different sense, and this is more true for, if you will, enterprise applications, there are typically regulations. There are typically requirements out there to prove that you as an operator, as a cloud provider, are following the rules. So the compliance space is also important. Lastly, with the cloud stuff, you are basically outsourcing the infrastructure, managing it, and good amount of responsibility for running the system to somebody else. And I'm using the term outsourcing very loosely here, guys. The cloud is highly automated and so forth. But nonetheless, you need some guarantee from the cloud provider on what is the service level expected of certain services. What are the performance guarantees? How many operations will succeed? What's the percentage of system being up and down and so forth? So you have to be, as a provider, able to provide these SLAs. And as a consumer, you have to demand them and know what you're getting as well. Okay? I will go through them in a bit more details, but I want to note there are many other challenges I'm not touching on today. For example, actually building and managing these very large systems is a big challenge. I believe we and a few others have been tackling it very well. There are a bunch of business model discussions, etc. Not for today, not for me at least. But those 4 areas I mentioned earlier, I spend more time on them right now. They're actually real issues that we are working through, and they're more in the same vein, if you will. Let's talk about the first one now. Targeting apps to the cloud, if you will. First, I have to admit there's some very easy cases. If you have a simple website, static content, let's make it very simple. Maybe a simple database, you can lift it almost as is and drop it in the cloud. People do this all the time, okay? And you'll see that in our platform, it's becoming very easy to do that kind of stuff. Don't get me wrong, there's a good amount of computing power in there, it helps with the scale, great. However, in many cases, this forklift approach does not work. You can't just take the app and run it in the cloud. For a number of reasons, to be honest. Note, I've been using the word app loosely here. In real life, applications are very complex. They're actually a graph of things that depend on each other. Which pieces can actually be moved, which pieces cannot be moved, and so forth. Some of the issues to consider are on this list here. Briefly, where is the application state? Does the application, for example, assume that its state has to always be local and the golden copy is local? You can't do that in the cloud. You have to put it somewhere else. You have to find a way to make it highly available in a storage system, for example, somewhere else, or rewrite the application. How does your application scale? Do you expect to call your favorite IT person and say, order an extra CPU and more memory for your application? Or is it actually a horizontally scalable application? And by the way, guys, I'm being very simplistic in my description here. In real life, it's more complex. You have to partition the data and so forth. There's a bunch of aspects to it. What are dependencies of your application? Is the standalone system, like a simple website where you just bring it up and maybe it has a small database in the back? Or is it a complex graph with dependencies on local systems, or maybe on some legacy systems, maybe on some storage system that we have here and there and so forth? Do you even know the dependencies of your application? You'll be surprised. Some more enterprise applications, the graph is very, very complex. It's even hard to find where to cut the lines. Along those lines, what are the connectivity needs of the application? Sometimes you have two components that you want to move them to the cloud together, which is great. In some cases, you have to keep one somewhere here locally, perhaps one remotely. Is the protocol chatty between them? Physics is physics. So you can't just put them in here and there and say it's going to work. You have to think of, do I have to re-architect a protocol, and so forth. And as I alluded to earlier, hardware needs here. If your app, your space, assumes something very special, you may not find it in a very large-scale system. I mean, I love some of the special hardware one can use to accelerate certain application sets, but you won't find these at scale until they become really more of a commodity play, if you will. So can your application be modified, or can it live with off-the-shelf, say, Ethernet, instead of ServerNet or InfiniBand or whatever technology you're of interest this week? Lastly, as I mentioned earlier, these systems are really hard. And any way you cut this thing, you end up doing some distributed system programming in the cloud. So the trick is to use CAN services as much as possible for that. Let's talk about security for a second. By the way, after I finish this section, I'm going to stop, then tell you really how we address each one of these as well. For security, as I mentioned earlier, sharing is really a key point here. You end up sharing resources from different applications, different executables. Data has to be stored in shared systems, so you have to isolate them. You have to figure out how to get to these resources. So an identity system, an access management system is needed, and enough policy controls to control how you get to those resources. And of course, all this stuff, you really have to demand it to be independently verified. You should. And there's standards out there, by the way. I mean, there's some alphabet soup here of ISO and SSAE and what have you, but they serve a useful function. If we're a third party, you can go and make sure that, yes, the cloud provider has been audited and they follow the rules and the like. For service level guarantees, generally speaking, they fall into two categories: availability SLAs and performance SLAs. And typically for something like an availability SLA, it's a ratio of how many operations of all the total possible operations that are guaranteed to succeed. Okay? So there's always some possibility of failures, guys. You know, there's a network in there and so forth. And you find things like 99.95% of the time, operations will succeed with this blah, blah. And there's also language in there. These can be hard to provide, but you need to ask for them, and again, the provider has to provide them. What's even harder to provide, especially in a highly shared system, are performance isolation and performance SLAs, actually. And you'll find that we don't actually offer many of those in general in industry, which is one of the challenges we have going forward. So performance SLAs, some of you in the room may be interested in this. You know, you may require that these two entities talk to each other with low latency. You want to be co-located, etc. And that's really not easy at the moment in a highly shared system. We'll talk more about this in a second. What you find that many in the industry provide nowadays are basically performance SLAs on a sort of a point, not to end-to-end, but only on a point basis. This virtual machine would have so much capacity to hit the network. It's an adapter, great. But nobody will give you an SLA from end-to-end within the network, for example, at the moment, or a latency guarantee, etc. We'll talk more about toward the end about this. Okay, so enough of the architecture and some of the high-level stuff. Let's get concrete now. What I did to recap is talk briefly about the cloud, you know, the value prop, what have you. Told you some of the challenges we see in the cloud, stemming from the fact that high sharing in a highly scaled system is needed. I'll spend a few slides to, just very few here, tell you what Windows Azure looks like, and then very importantly, map these challenges to how we actually solve them, are solving them in Windows Azure, okay? Some pictures. Think of Windows Azure as an operating system in the cloud. It's a very highly scalable system, runs globally, gives you a bunch of services. I'll give you some list of those in a second. Allows you to program your favorite programming language, your favorite programming tool. And the whole idea is that by having enough in the platform, in terms of services and ability to manage your applications, to make your life easier. It's in a nutshell, guys, okay? I think many in the room have been programming the system, so I will not spend much time to explain the basics of it. Key to it, though, is, and this follows on from the earlier slides, given its scale, we have to automate. So behind the cover, everything in the system actually is highly automated. Behind the cover, we structure the system through these separate units of computations. These are very large-scale clusters, each of which is controlled by a smaller cluster of so-called fabric controller. And a fabric controller is basically the brain of Windows Azure. And the whole main loop, if you will, for managing Windows Azure is that you ultimately submit to the system a big description of your application. It's a fancy XML graph, by the way. You do it by hand or through one of the tooling we give it to you. That XML file is basically ends up being consumed by our system. It describes logically what the application needs in terms of a network topology. We take this network topology, we have all the physical topologies in the system, and we map them. Basically, all the fabric controller does is takes a logical description from you, looks at the physical inventory it has, does appropriate mapping, provisions the systems, all the way from between the machines, OS, etc. Very importantly, setting up all the virtualization boundaries within the actual servers, and very importantly, in the network as well. From there on, we do basic monitoring of the application to maintain the status quo, to maintain the logical model that we got from the user. If something goes wrong, there are basic health model activity that we do to restart, during which we replumb all the plumbing to make sure it's as transparent as possible. You get an event, of course. And ultimately, there are cases where automation does not work. You have to do something about it. I'm way oversimplifying, but the key point here is that everything I told you is automated. We don't have people just watching monitors for every possible deployment coming in and out and so forth. We will never scale like this. A few more points here. All the services that we expose in the system, and you see a slide in a second, are available following the basic architecture I told you earlier as a bunch of open REST APIs. So everything in this system, from the way you submit or deploy applications to monitoring them to access the resources like storage, are through RESTful APIs. Yes, we have programming languages, help, and so forth, but this is really a web platform here. You can hit the application from within the cloud, from some third-party cloud, from on-premises, from your local device, whatever the case may be. Globally, we are in 8 locations. Actually, it's a new slide. We just added 2 locations a few weeks ago. It's actually a major asset, by the way, in that we are in North America, Western Europe, and Asia as well. That choice of location is a policy that you decide, both for computation and for storage. You can mix and match as you see fit. These are large-scale data centers. They are globally interconnected through a global network. And also on the slide behind me, if you notice, there's also an optional CDN network, a content distribution network as well that you could use for applications. It's optional. So remember the slide? I'm going to just, for each box, I'm going to tell you what we actually have done in Windows Azure. So for virtualization, every physical box has a hypervisor. It's based on Hyper-V, which is a commercial hypervisor we have. It's responsible for dividing every server into a bunch of VMs. One VM is trusted, runs our software in it. The rest are guest VMs that are untrusted. They run whatever payload comes from the user. The payload could be a simple, high-level piece of code, like a web payload, if you will, all the way to a full VM. Now we have different models in that. In that trusted partition, if you will, is where we do our, for the second box now, our network virtualization at the edge. When I say the edge, think of the network itself and all the trusted partitions in the system. That's our edge. That's where we enforce the network isolation boundaries between the various VM graphs in the system. So you may have an application, you may have an application, we have an application. They're all laid over the same physical infrastructure. Those logical graphs with their isolation are enforced by the network overlay network, basically. Okay? We do more network virtualization, by the way, between on-premises and the cloud. Maybe later on I'll mention it. But again, the key point here is that effectively it's an overlay network. For Scaleout, as I mentioned, everything is based on the VM boundaries. We have a fixed set of VM sizes. They may change over time. But the point is, it's a scale-out horizontal scale model. Everything in the system, everything, optimizes mean time to recovery. We expect your apps to be written that way. We have written our infrastructure that way. Our hardware model is like that. Everything is like that way. And it takes a way of, actually it takes time for people to think this way, guys. But everything is optimized for mean time to recovery. Even the way we operate the system and where we have to intervene to fix a problem and the like, keeping the live site up is #1 priority. Optimizing for mean time recovery is #1 priority. Then you can go and maybe figure it out if you have to and so forth. For caching, for viewing the node as a cache, there are 2 basic mechanisms here. One is we do have a network drive, effectively, and externalize durable network drives. So if you have to write through classical application off the shelf, like writing your local file system, you're actually writing a remote volume. Okay? This is key. The remote volume in turn goes to a storage system, which is highly replicated and so forth, but the writes are durable. Anything else you have in a machine, which you have access to local logical drives and so forth, are a cache. You know what I'm saying? So you can cache as much as local as you want to. We will try very, very hard to keep the cache for you as long as you're running. But ultimately, physics can come in, it can crash. You have to be able to go remotely, of course. If you happen to be yourself implementing a highly durable storage system, some people do, you effectively are using these local drives as your local replica, by the way. And depending on the fact you have other replicas in the system to get your durability. Okay? For automation, I already mentioned earlier, this system is model-driven. So all the provisioning actions, all the actions to recover, restart application, and so forth, go back to the logical model that we get from the application developer or the tooling that they provide. So all the automation I mentioned earlier comes in from that logical model. And the model, by the way, describes the topology of the application, basic resource requirements, and also scalability aspects. And you can change them on the fly. We change the number of machines and so forth behind that number. Lastly, and I'll show you the next slide on this one, slide 2 on this one. We have a very rich set of services, guys. I mean, most of my talk was about the plumbing, the platform, and so forth. But frankly, going forward, much of the investment really is in all these services. See, our vision at the end is very simple. I want you to be able to fire up your favorite programming tool, either Microsoft Visual Studio, Eclipse, or what have you. Write as few lines of code for your application and otherwise compose everything out of services in the cloud. And you can use my services, you can use third-party services, I don't care. But the point is we need to up-level level of abstraction here, guys. Because as I mentioned, most of us don't have time or even the ability at times to do very complex distributed systems. Okay, so I'll go quickly through. I told you how we mapped architecture principles to what we have built. For each one, I'll tell you what we actually have in there, and you'll see a bit more details in the platform now. For application development, this slide behind me is what the industry likes this week. Okay, I'm not a big fan of it, but it's how we speak of it nowadays. We have so-called infrastructure as a service, which is, in industry speak, is you get a bunch of VMs, do whatever you want to. So-called platform as a service, where you have a lot of services in the platform. All these services you can actually call into. And you get automation and management of your operating system stack and so forth. And so-called SaaS is software as a service, typically the end product. Where we fit in the spectrum is Windows Azure design point is very much in this part. You can build your app to use both concepts. As a matter of fact, you mix and match them in the same application, between applications. You may have some legacy code you want to bring in a VM, go for it. You may want to write new code or port new code to use full capabilities of the platform, go for it. This is what the platform is about, is making it easy for you to write your applications or port your application to the cloud. Around this part, you end up doing things like you can go build your own systems on premises. You can use Microsoft technologies. You can use some other third party. By and large, though, you find your scale point to be much, much smaller here. You get all the control you want to. You want a connection to a fiber channel array, go for it. You want to talk to a mainframe legacy system, go for it here. So here you can customize. You want InfiniBand with the latest hardware, go for it. Here you'll find us more over the scale points I mentioned earlier and uniformity points I mentioned earlier. And lastly, what most people end up with this platform doing is produce these things, the finished services, if you will, the thing we consume from our phones, from our laptops, from our tablets. So you have the plumbing. You have a bunch of services, either very basic VM running or a bunch of other higher services around that produce these high-level cloud services. Now, we all know about this side of the spectrum, of course. You have virtualization on premises and physical systems and so forth. So our emphasis has always been make it easier to get apps to the cloud. And to do that, you have to have tooling. You need to have support for programming languages. Now, just to be very clear, guys, you want to write something in assembly language on this platform, you can. We have one big customer. They make good business porting COBOL programs to this platform. Okay? I'm not saying you should do that. But my point is you can bring your favorite programming language to this platform. Having said that, we make it easier with a number of SDKs, development tools, toolkits, libraries, with all the stuff you can think of to write to this platform. So we have very good support for .NET, Java, PHP, Node.js. We have SDKs that's specific to certain domains, mobile, for example, for all the mobile phone platforms, all your favorite ones, etc. Programming tools, you can use a Microsoft tool, .NET, from the lowest possible configuration to the high-end ones. And of course, you can use Eclipse with Java and other languages as well. If you don't want to use any of those tools, go for it. Download the SDK, use command lines. Have fun, not an issue. The point is, I keep emphasizing here, is that we recognize that people have code that exists, and they are programming tooling and languages that exist already. And you can bring whatever you want to this platform. Now, this is a busy slide, I guess by design, to impress on you that this platform has a rich set of optional services and building blocks for your application. No, I'm not going to go through every box here. Every box is an hour or two of talk, if you will. Each box behind me, most of them at least, are large-scale distributed system problems solved for you. There's, for example, behind me, the basic storage services stack in there. You want to store a petabyte in Windows Azure? Go for it. You want to have very large blobs of 1 terabyte each, or 10 terabyte each, or 50 terabyte each? Go for it. You want to have very highly structured relational database system as a service? Go for it. We have one of those as well. The point is, there's a number of rich services in the platform here. Virtually everything behind me exposed to our REST APIs or your favorite programming language. You can mix and match, and this is key to make it easier to actually program for these systems. As I keep saying, most people have difficulty programming very large-scale systems. So the more they depend on existing services, the easier their life could be. Again, you don't have to use any of this stuff, but I recommend you do. Default is in 6 separate categories. Services that help you with running your application, management of your application lifecycle, basic storage infrastructure, that large petabytes, NoSQL infrastructure, if you will, a SQL database as a service, support for security and isolation, identity, federation, single sign-on, a number of these scenarios. Integration, particularly if you have code on-premises or code that you have to go to third parties and so forth, like durable messaging, queuing, and so forth. And lastly, networking, both within the cloud and between you and the cloud, especially if you live behind a firewall and you want to have certain policies for controlling access to it. Guys, the platform is rich because the applications that run on it are actually quite diverse. So you end up basically mixing and matching what you need. Now, I keep talking about sort of writing the application. You actually have to manage the application too, right? So it's one thing to write an app and say, hey, it's running. You have to actually be able to watch it and see it and so forth. So there's a bunch of tooling here, from the actual web portal, which is quite rich, quite easy to use, to the underlying APIs, which are REST APIs for managing applications. But all our tooling, the web portal, the third-party tools, our in-house tools, use the same APIs. So if you don't like the portal, fine. Don't use it. Use the APIs if you want to, etc. And the third parties out there are already using the same APIs as well. That's a basic strategy we're following, if you will. The APIs are available, they're open, and we build tooling on top of the whole thing. There's a set of problems that some of you may face where you have to connect your assets, your applications running in the cloud, to somewhere else. You may have to connect them to a network you have on premises in your lab behind a firewall, in your enterprise, whatever the case may be. So we have a number of services that were actually in that previous slide I mentioned earlier that aid in this function as well. Yeah? And they start from the lowest level. For example, think of VPN on steroids. that this is a service to you. You just say, I want that part of the service to connect securely to this access on premises, all the way to services to help you with data synchronization and managing where data really resides in there. Okay? Anyway, offline we can discuss the details here, but there are more of these as well. Talk about security a bit. Discussed how compute isolation, if you will, the basic virtualization in every machine is really key. And as I mentioned, we have the basic hypervisor, which is trusted, and we do have a root OS, the main partition, which is also trusted. It's small, locked down, etc. And in it, we run our software, if you will. That's responsible for the network virtualization. The rest are a bunch of guest VMs, and they are not trusted. And you know what that means, really. We can effectively run any VM as far as security is concerned. Network isolation goes hand in hand, and the way it works is we basically do also packet filtering at the network edge as defined as at the root OS. And the network packet filtering, basically, we end up with an overlay network here. So your application thinks it has the whole network. It may even see its own local IP address range, for example. But it's actually shared over a lower infrastructure in there. And as I mentioned, the brain of the system, the fabric controller itself, it's actually running on a bunch of machines in the cloud as well. There are extra measures of isolations for it. For example, all communication between it and any control software it has in the cloud itself is SSL, mutual authentication. We have encryption. We also have support to help, for example, with key management, distributing secrets. Your application may have its own secrets, by the way. So we make sure that we store them in the right way, distribute them in the right VMs, recycle them, and so forth. We have much of this is already documented, by the way. We have a security white paper, for example, et cetera. So this information is out there in the public. And to give you an example, the basic model we have of authentication for the base platform here, guys. And for the sake of time, I will skip the slide. But again, all the stuff is documented offline. The point I'm trying to impress in you is that at the foundational level, we have taken care of all the bases. And the movement now is to move up the stack and add more services over those foundational bases. Everything runs in highly secure physical infrastructure, data centers. We sort of take this for granted, that nice picture I showed you globally. But each one of those is actually a bunch of data centers that are physically secure. They have their own physical security aspects and who can go in there and so forth. I can tell you for myself, and any Microsoft employee here, we can't even go there. I cannot even touch the machines myself. I cannot touch them physically nor even logically. We have also controls in there as well. These are very important because we can all invest, if you will, in the computer science problem, isolation, virtualization, and where secrets are and so forth, but a breach of other kind of nature can be a big, big, big problem. So we have to cover the whole spectrum, from the hard problems to perhaps some of the even harder problems here as well. In addition, let me just touch on a couple of things here. Geo-distribution. It's important that your data is not only is highly available within the data center, but it's also available in case of the small probability of the data center itself being inaccessible. So for example, writes in our storage system are replicated 3 times within any given location. And it's also asynchronously replicated geographically to a remote data center as well. That's part of the platform as well. You can opt out if you want to, but most people don't opt out for these things. There's more, of course, for disaster recovery preparation and the expectation of the application and how they can recover from it as well. And again, we have white papers on this stuff and some details online. Compliance. The following may sound a bit dry, guys. Hold with me. Okay, I have only one slide on this. But it's actually very important for a large-scale cloud system to actually make it in the marketplace. Busy slide, I know. It has really one message, to be honest. Out there, bunch of industry standards and regulations. Every country has a bunch of them. Every industry has a bunch of them, all over the map. If you look carefully at them, however, you'll find out there are a lot of commonalities between them. So what we have done is, forget the alphabet soup for a second, the actual standard names and the like, is we look carefully at, we built a framework basically, a controls framework that covers all these kind of regulations out there. What this means in practice, by the way, is our system has a lot of logging, auditing, processes for touching the system, for touching the hardware, etc. We basically generalized what all these compliance regimes require. And we built them in the platform. Out of that, we end up obtaining certain certification attestations as the market dictates. Okay? That's the only way one can keep the sanity, to be honest, guys. Because otherwise, if you look at all these regulations out there, the big, thick documents of stuff out there. There's actually good uses of this stuff. I mean, we should all learn from them, I believe, on how we even manage our own software. Who can manage it? Who can update the software? How often do you do that, and so forth as well. And everything, of course, is done through an audit schedule as well. So we have to be audited. All of us do, all our processes and the like. It's a fun space, guys. It's not the same as the old enterprise software where we used to write a piece of software and ship it, if you will, and somebody else cares about the stuff. Now we have to develop the software and actually run it and audit it as well. Almost done, guys. For SLAs, a bunch of SLAs, though you'll notice something behind me. These are mostly availability SLAs. We don't have performance SLAs really, by and large. Some exceptions here and there. You'll find that in our industry at large, there are no performance SLAs really. Yes, we will tell you that for a certain VM size, you get so much capacity and so forth, which is a performance statement. But there are no end-to-end, at the moment, performance SLAs in the industry at large, guys. Typically, the answer is, if you really care about, I want latency to be so many microseconds or milliseconds from here and there, frankly, the only way to guarantee it is to build your own hardware. Or you go do a custom make something as a hoster, if you will. So we are very competitive with the industry here as far as availability SLAs, as SLAs in general, if you will. But performance SLAs, all of us have some ways to go. Which leads me to my last slide. There are a bunch of challenges really remaining out there. And we actually would love to collaborate with many of you on some of those. One is, to segue from the last slide, is network performance guarantees. Effectively, end-to-end performance guarantees, I guess. Just think about it. The problem is we have to overlay all these separate graphs on the same physical infrastructure. Your graph is one application, your graph is another application. I want to guarantee you X% of the network and Y% of the network. How do I do that? Okay? There's literature has a bunch of ideas. We have ideas and the like. This is important so we can offer differentiated services to customers and a way to guarantee the performance perhaps over time, forever, whatever the case may be, for a given application versus another application. So that's one problem space, if you will. Another one is, of course, optimizing large-scale computing over data. Shipping computation to data, probably not the other way around, but you want to do MapReduce over your large data store in a highly shared system in a secure way. There are security aspects here you have to do. How do you sandbox that? How do you make it very, very fast, if you will, doing so as well? Now, we all know literature all over the place, but please place it in the same context I'm describing it here today, which is a highly shared system. And you find out there are problems with isolation that, oops, the only way I can do this thing, I have to copy the data here, copy computation there, do some stuff on the side. But copying a petabyte is kind of slow. So what do you do? The first 2 points were mostly about mechanisms. We are increasingly noting that we must employ more economical models in how we apportion, price, and give resources, manage resources between customers here. Again, there are a bunch of papers on this. We actually have a huge system that requires this. I personally find the intersection of economical models and computing very, very interesting. And more importantly, perhaps, I also I believe that now we found out we actually need stuff. Before it was nice ideas, now actually the stuff is really needed. Lastly, and this should be self-evident, I mean, there was some work at Berkeley a few years ago as well. Machine learning can come to a rescue in to many things. And here we have very large systems. Very large systems, guys. We don't volunteer the numbers, but we're talking very large system here. The number of events we can generate out of it is quite a lot, from the actual software, hardware, customer events, and so forth. So it would be great to be able to apply machine learning, to do things like error prediction, root cause analysis, trend analysis, what have you. Yes, we have also telemetry and the like, but it would be great to know problems before they happen and stuff like that as well. Okay, guys, I should stop talking because I'm sure somebody has some questions. I hope so. I'm almost out of time, but if a couple of questions perhaps, guys. Thank you.
So we got started a little bit late, so I think we could push our break back a few minutes. We have some questions. Hang on, we've got to use the microphone so the people on the web will hear your question.
Hi. This is a question about the uniformity of the compute platform. So TCO-wise, there's a trend to many core computers, and the question is whether the assumption that you have many small computers forming the cloud will remain valid over time, or whether cloud rather becomes a set of clusters, so a network of multi-computers.
You dropped off at the end, or becomes a set of clusters,
yes.
You're saying?
Yes. And follow up, once we are there, then you want to think about co-location, and you want to develop vocabulary to express this. So what is your comment with respect to that?
So let me just note a few things. First, we strive to give a uniform model, and I believe in general the industry will strive to provide a uniform model. But as you know, it's just the physics of acquiring machines and retiring machines. Behind the cover, we do have heterogeneous systems. Just time. I mean, we started this project 5 years ago. You know how this goes. So we end up with a level of abstraction to, as much as possible, give you a uniform system. The forces to make it not uniform include what I mentioned earlier, the fact that we have to buy machines and retire machines and so forth. Includes desire by some customers, many customers perhaps, to have specialized systems. Maybe more memory, faster networks, maybe GPUs, etc. I do believe you see a bit more heterogeneity in these systems. You will see some, don't get me wrong. But you will not see customization or customizability, if you will. You know what I'm saying? And I'm being qualitative in my discussion here. So as things like GPUs become not just cheaper, but less power hungry and not as hot, that's a problem with them, by the way. You may see them more and more as production systems, for example. Same with maybe special networks and the like. Whether we expose them as a cluster boundary versus something else, probably not a cluster, as I mentioned earlier. When I mentioned the word cluster earlier in my presentation, I showed you something behind the cover. That's our unit of allocation and containing certain boundaries and so forth. What we'll probably strive to provide you is with the specialization you want within a fixed set, regardless where the boundary is, as far as we are in the same latency, boundary, if you want, the same data center. So you won't be given a cluster for you this time versus the other time. The time multiplexing that way would not really work very well for us. Now, this stuff is early, to be honest. In the limit, if the scale becomes even more than what we're thinking of, yeah, maybe we can give you a whole cluster for a while, for example. I want to note that there are enterprise scenarios where people who want to commit resource allocation for a longer time, who want to have more control over their boundary. And those models may actually happen in industry as well. We'll see. Stuff is new.
Any other questions? Plenty of time.
I have a question regarding the targeting application to cloud that you mentioned. You mentioned that we need to consider lots of the question. But Azure, when he was developed, it's tried to make people feel that we can use that to develop many applications.
Mm-hmm.
But it seems that to me from your talk that he need to be very specific or some niche, and not many applications like the mobile phone can take advantage of this.
The question is about targeting apps to the cloud, and is it a niche application system or more general?
Yeah.
If anything, it's actually quite general. I mean, I skipped some marketing slides I can show you, but we have a wide spectrum of customers, from people who do very simple websites, support for mobile phone to tablets, high-performance computing, and heavy-duty enterprise customers. So the answer to the question is, I showed you sort of a bottom-up view by design to tell you that we have support for multiple models, if you will. And you can, very importantly, mix and match them as well. So you mentioned by name mobile, for example. If you want to only think about mobile, we actually have a development kit, a bunch of libraries and the like, to make you just worry about your mobile problem with a backend for your favorite mobile operating system. Or you can do it all the way down to take some legacy code and run them in a VM. All these are available. Mm-hmm. So we have verticals where if we were having a dialogue only about, say, Windows Mobile or iOS or something, we can speak that language only. Okay? Yeah. But by and large,
so basically, it can be used for the general.
It's an OS,
okay.
You know. But the problem with OS is that there's just a bunch of plumbing. You have to have the other stuff on top of it.
Can I ask another question? Is regarding the performance.
Yes.
When we use the Azure as a platform to develop the software.
Yes.
But how can we know the threshold we can achieve a better performance compared to we use the on-prem, the separate individual server?
Sure. So the question of performance and how do you know that?
Yeah.
You know, the easiest way, to be honest, is to run something and measure it. We strive to give you a uniform performance regardless where you land in our clusters. Okay, that's kind of important to us. It's part of the uniformity model we strive to do. So by and large, you should get uniform behavior, although I have to admit sometimes you may get different behavior depending where you land in the system, if you will. But the short answer, the best way is to actually go around and measure it yourself. Now, we have monitoring infrastructure support, and there's new stuff coming as well to make it easier to monitor your application. But you're in the best position to do a comparison between, say, hardware you have on premises, if you will, and something in the cloud. But if I may up the answer just one level up, if you just want to run a simple computation on a machine, you may want to just use your local machine, to be honest. If you want 1,000 VMs or 200, or you want to write a very sophisticated application or use our storage system and the like, that's what the cloud is really for. If you want a lower presence, that's what the cloud is good for. You want to integrate between different pieces. You know what I'm saying? So there are some cases where, yes, you can use it to host a piece of computation in the cloud. That's great. But usually with scale, the bigger your application needs, or the more sophisticated the connectivity needs are, or the global presence you need, the more useful the cloud will be for you.
Sushil Prasad from Georgia State. Regarding your second bullet there, in terms of large-scale data and computing, what do you see forthcoming, or what is the projection in terms of co-locating computation and data, maybe pre-processing data, distributing it, all those issues?
Well, at the end of the day, it's physics, to be honest. Especially when we have large data, it should be easier to send computation to a data versus the other way around. Okay, we all know that, if you will. So if you have large data sets, shoveling them around just to run in a VM, if you will, separately from the rest, is very cost prohibitive. The tension here is that if your data set is part of a shared infrastructure system, I'm saying a big storage system, for example, right? And you want to be able to compute close to it. How close can you get while yet still being isolated from everybody else in the system? You can get very close to them in the network. Maybe this machine talking to this machine, we should be okay. Can you run securely on the same server that's providing your data, for example, in a highly shared system? To do that, you have to have the appropriate security model as well. And so there's a spectrum in there. And that spectrum has also different cost models as well. So we can talk offline if you want about some of the options in there. But it's, the The building blocks, we sort of know what needs to be done, but to put them all together is not that easy yet.
So I think at this point we could take it offline, as Joseph said. He's going to be around here. I'm not sure how long, but
I will be.
Okay, and we've got a break now, and I would suggest, since it's 10:07 now, we start up the next session 7 minutes or so late, or say 10:40 we'll start up again. So take a break, and Joseph will be around. Thank you again, Joseph.